Welcome to another jam-packed video on random variables. In this video, we're going to focus on combining random variables, one of the most important topics when it comes to random variables. If you haven't watched my video over transforming random variables, highly recommend you do so before watching this. Or if you haven't watched my video over the mean and standard deviation of a random variable, hopefully watch that one too, because everything in this video is going to involve finding the mean and standard deviation. All right, so let's just dive right into it. So first off, what the heck do we mean when we say combining random variables? Well, we actually mean one of two things. We either take two or more different random variables and put them together. Like, let's just say there's a mean time that it takes me to wash a car, and there's a mean time it takes me to wax a car, and I want to put those two things together for the total time to wash and wax a car. But careful though, when you put two random variables together, they do have to have the same unit, because you can't add things that have different units. So either make them the same unit, or if they're completely weird different units that can't be combined, then you can't combine them. But the other thing combining random variables represents is taking one random variable and repeating it. And we're going to talk more about that in an example here shortly, but it'd be doing the same random variable multiple times. So again, if I have the mean amount of time it takes me to wash a car, and I'm going to wash 7 cars in a row. So I'm repeating washing a car, washing a car, washing a car, washing a car. That's another way that we talk about combining random variables. This is not transforming random variables. Again, that other video dealt with just simply converting the units of a random variable to a new unit. Totally different topic. This is much different. Now, we actually know how to combine variables in algebra, right? In algebra, when we combine variables, we do something like this. Hey, variable x plus variable y, and that's x plus y, because we know that those are not like terms in algebra. So we can't combine them because they're different terms. But if they have the same unit, then we actually can combine them as random variables. And sorry for that little, it says, but we can here if the same unit. So sorry, there's all that extra space in there. But the idea is if they have the same unit in random variables, you can combine them, whereas in algebra, if they're two different terms, can't combine them. All right, then we also have this idea of repeating the same random variable. So again, random variable x plus x plus x plus x. Now in algebra, that's 4x, not x to the fourth, people, right? X plus x plus x plus x is 4 times x. So this is certainly true in algebra, but we do have to be a little bit careful with how we do that, especially when we're working with standard deviation. And by the end of this video, you're going to know exactly what I'm talking about. So without further ado, let's dive into some examples where we are combining random variables. Now, for most of the examples that we're going to look at in this video, we're going to use these two generic examples. So the mean of random variable x is 10. That means in the long run, we would expect random variable x to have a value of 10, but it could be a little bit more, could be a little bit less, because random variables vary. And the standard deviation for x is 1.7. Really notice that subscript x there to deviate between the two. Then the mean for a second random variable is 15.6. And of course, that random variable also varies, so there's a standard deviation there as well. Now, these problems, there's no context here, so if you really want to add some context, maybe we could just say that both of these are in meters. So all of this is in meters, because they do need to be the same unit if you're going to combine them together. All right, so now let's talk about combining random variables and how that actually impacts the mean. This is the easy part. Like, this is so unbelievably easy. All right, so when combining two different random variables or repeating a single random variable, you simply add the means together or subtract them if you're asked to look at the difference. So again, it's literally this easy. Like, I can't make this any easier. So if you're saying, hey, I'm going to do x and y together. I want to find the mean of x plus y. So notice my symbol here, the mean of x plus y. Well, the rule is very simple. All you got to do is take the mean of x plus the mean of y. So I'm going to take 10 plus 15.6, and I don't even need a calculator for that, 25.6. And again, it would be the same unit. So if I'm in meters, then this would stay meters. I mean, come on, how easy was that? Now, if I'm going to repeat random variable x 4 times, so I'm going to do random variable x once, second time, third time, fourth time, maybe this represents like how far somebody can throw a shot put or something, and person X can throw it on average 10 meters, so they're going to throw the shot put 4 times, and we're going to add together to get their total distance. So again, I'm simply saying, okay, well, that would be expecting 10 for the first throw, 10 for the second throw, 10 for the third throw, 10 for the fourth throw, and yeah, that's pretty easy math to do, 40 total meters. Now, obviously, I could have done 4 times 10 and gotten that answer of 40 a lot faster, but I know you might not like this, but for random variables, it actually makes sense to just go slowly. The first plus the second plus the third plus the fourth, because there is a difference in terms of doing it 4 times, whereas just multiplying by 4. Because if you watch that video on transforming, when you're transforming, you just multiply by the conversion factor to convert it. But when you're combining random variables, we want it to be clear that we're actually doing that random variable 4 separate different times, them adding all together. But listen, I'm not going to fault you if you do 4 times 10, as long as you understand that I'm doing one random variable 4 times. All right, what if we're looking at the difference? Because sometimes you might say, hey, what's the difference between those two variables? Oh, person X throws it this far, person Y throws it this far. What's the difference between them? Well, the rule here is pretty simple as well. You just find the difference between them. Like, I can't make this more complicated. So if I'm trying to find the difference between X and Y, the mean difference that I would expect from X and Y. So if X throws the shot put, Y throws the shot put, what's the difference I expect? Well, all I got to do is take the mean for 10 minus the mean for Y. Now, I am going to get a negative here, negative 5.6 meters. So just make sure you understand what the negative means. The negative doesn't mean that you have a negative distance. That's impossible. It's that we would expect X to be 5.6 meters less than Y. Obviously, we could do this in the other order. I mean, there's nothing stopping us from doing it in this order, where I would get a positive 5.6, but that doesn't change what happened. That would just be person Y is 5.6 meters better than person X, but that's the same thing as me saying person X is 5.6 meters less than person Y. As long as at the end of the day, I know who's more and who's less, it doesn't matter the order you subtract them, but you are going to get a positive versus negative, obviously. All right, so again, pretty easy there, like not trying to overcomplicate this at all. When you're working with means, combining random variables, it's so unbelievably easy, you just kind of use common sense. But unfortunately, all that's about to change when we're working with standard deviation. So how does combining random variables impact the standard deviation? All right, this is where it gets a little bit tricky, so I hope you're paying attention. For the examples, I'm going to use these exact same numbers that we've been using here. But now we're going to be looking at the standard deviation because, go back to here real quick. Yes, I expect the total for X and Y to be 25.6 meters, but that total could be more or less. So there's going to be a standard deviation with that total as well. All right, now before you start looking at my rules and getting a little confused, just hear me out. There's 2 rules here. Rule number 1, you cannot add standard deviations. Listen to that one more time. You cannot add standard deviations. Don't ever add 2 standard deviations together. Oh my gosh, don't ever do it. Rule number 2, you can add variances together. You can't add standard deviation, you can add variance. So now if you're wondering, okay, I'm going to need a refresher on variance, well, here we go. Variance is simply standard deviation squared. That's it. If you take the standard deviation and you square it, you have variance. So variance is literally, so sometimes we just use VAR to represent it. In math, we always love shortcuts, right? So VAR is just taking the standard deviation of a random variable and squaring it. I tell my students, you actually don't even have to square it. Now, you can, obviously. I hope everybody knows how to square a number. But just putting a square on the standard deviation instantly changes this to variance. So sigma is the standard deviation symbol. Sigma squared is our symbol for variance, literally just taking the standard deviation squared. So I'm not allowed to add 2 standard deviations together, but I can add 2 variances together. All right, so if I want to find the standard deviation of X plus Y, so I'm combining X and Y, and I know that that total is 25.6, but that number could deviate, I can't add the standard deviations. Do not add 1.7 plus 2.3. You have to add their variances. So I'm going to take the 1.7 squared. Again, don't even do the math. I don't know what 1.7 squared is, to be honest. Off the top of my head, I have no idea. But just putting that little square on it, now that's variance. And the variance for y is 2.3 squared. Just put that little square there. Boom, you now have variance instead of standard deviation. You are allowed to add variances. So now this is the variance for x plus the variance for y, but now I have total variance. Now, I don't want variance, I want standard deviation. So if you have your total variance, how do you get back to standard deviation? Well, you square root. I mean, think about it. If I want to go backwards here, I'm going to take the square root of each, and then all of a sudden the square root of variance equals standard deviation. So once I add all of my variance together, I have my total variance for these two events, x and y. I do need to put a giant square root around all of that to get back to my standard deviation for the mean. Okay, so let's actually go to the calculator to do this. So I'm actually going to type in exactly how as I wrote it. Square root 1.7 squared plus 2.3 squared. I mean, I never actually need to know what 1.7 squared is. I don't care. The calculator is going to do all that heavy lifting for me. Just make sure it's all inside the square root, and boom, there we go. Now, I'll get kids that will be like, no, wait a minute, Mr. Prenchak. That's the same thing. That 1.7 plus 2.3 is the same thing because squares and square roots cancel. There's proof that that's not true. Squares and square roots do not cancel when there's a plus sign in between them. So don't you dare try to tell me that they're the same thing. That is the importance of making sure we understand why you're not allowed to add standard deviation. You have to add the variance first, square root it to get back to a standard deviation. So my standard deviation for the total of x plus y is 2.86. And if I'm in meters, that's also in meters. Okay, that's huge. Hopefully you understand that. All right, what if I were to repeat random variable x 4 times, right? We would expect the mean to be 40, 10 plus 10 plus 10 plus 10. 40 is the mean. What about the standard deviation? Well, once again, I'm not allowed to add standard deviation. So I am allowed to add variance. So for the first occurrence of x, the variance is 1.7 squared. For the second occurrence, the variance is 1.7 squared. For the third occurrence, it's 1.7 squared. For the fourth occurrence, it's 1.7 squared. I'm not allowed to do 1.7 times 4 because, listen to me when I say this. Multiplication is repeated addition. So if I think I'm just going to do 4 times 1.7, yes, in my head I'm multiplying, I'm not adding, but remember, multiplication in algebra is repeated addition. So if I just do 4 times 1.7, I'm actually adding 1.74 times, and you're not allowed to add standard deviation. That's the #1 rule. So I have to consider the variance for each occurrence of the random variable x. Yeah, it's all the same, obviously. And then I have to put a giant square root around all of that to combine all of that variance together, square root it all to get back to the standard deviation. Now, once again, I know that 1.7 squared repeated could be written as 4 times 1.7 squared. Like, I'm okay with understanding that. I have 4 variances, but I don't have 4 standard deviations because I just got done saying you're not allowed to multiply 4 times the 1.7 because that would actually mean you're adding the standard deviations, which you're not allowed to do. So, but again, after you get all of that variance, make sure you put a giant square root around it to get back to standard deviation. All right, so let me show you on the calculator here. I'm going to type that in. So I'm going to start with the square root. Again, I'm not going to do it in steps. I'm just going to let the calculator do it all at once. So I have 4 times 1.7 squared. Now you could actually do the 1.7 squared plus 1.7 squared plus 1.7 squared plus 1.7 squared inside the square root as well. This does make it a little bit faster to type, but there we go. I get a standard deviation of 3.4. And again, whatever the unit of the problem in would be the same unit if I'm just saying that that's meters. All right, so if I'm going to throw a shot put 4 times, and I expect 10 meters each, 10, 10, 10, 10, 10, I expect a mean of 40 meters. But again, every time I throw the shot put, I could throw it a little more, throw a little less. So that's why there is a standard deviation for the total of 4 tosses, and that would be the 3.4. All right, hopefully that makes complete sense. But wait a minute, we actually have a third rule. This one's really important. Variance always builds up, or adds. Building up is adding, even if the problem is asking for the difference between two random variables. This is a forgotten rule. A lot of kids don't pay attention to this one. So if I'm looking at, hey, what's the difference between X and Y? Okay, to find the mean, it's literally this simple. You can't mess that up. So I expect a difference of negative 5.6 meters. But what about the standard deviation of X minus Y? Even though the problem is focusing on the difference, variance always builds up. So I'm still going to do the 1.7 squared, that's the variance for X, plus the 2.3 squared, that's the variance for Y, and then I have to square root all the variance, because square rooting variance is how you get back to standard deviation. Even though the problem is focusing on the difference, I still add standard deviation. Standard deviation variance always builds, even if you're looking at the difference. Why, you might ask? Because I'm still looking at two things, right? Even if I'm focusing on the difference between those two things, I'm still looking at those two things, and each of those two things could vary. That way, the variance is never going to go away. Variance never dissipates. It always builds up. So it's just a rule. I hope you understand it, but if you don't, then I don't know what to tell you. Look up more explanations, but hopefully I give you a halfway decent one there. So I'm actually not going to get anything different than I got when I was adding. It's going to be the same because variance always builds. So I'm back to that 2.86 for my standard deviation. All right, let's just dive into one more kind of final example here. This is a cool one that we oftentimes see something similar to this on the AP Stats test. So let's just say that we have 3 items. We have a plastic bin. And that plastic bin on average weighs 15 grams. But you know what? Sometimes, in the process of making a plastic bin, it could be a little bit more, it could be a little bit less. Even if the plastic bins are all identical, even if you look at 100 identical plastic bins, just based on the process of making them, they could be a little bit more, a little bit less in weight. So there's a standard deviation there as well. Then we're going to look at a Hot Wheel car. Hope everybody knows what a little tiny Hot Wheel car looks like. They come in all different shapes and sizes, but the mean of all Hot Wheel cars is 5.4 grams. And we all know some Hot Wheel cars are smaller, some are bigger, some weigh more, some weigh less. Of course, the standard deviation is there as well, 0.7 grams. And then we also have a mini monster truck. So imagine, I don't know if you've seen them or not. My kids have tons of them, but it's like a little, it's not a car, it's a little monster truck. And they're a little bit bigger than a Hot Wheel, so they weigh a little bit more. On average, they weigh 9.4 grams, but as well, sometimes there's a little bit more detail on one or another that might make it weigh a little bit more or a little bit less. Okay. So the standard deviation there is 0.2 grams. Now, this problem was inspired from my son, who has a plastic bin at home filled with Hot Wheels and monster trucks. So here's my question. Let's say that we have a plastic bin, and that plastic bin is filled with 5 Hot Wheel cars and 3 monster trucks. What do I expect the total weight and the standard deviation for the total weight of that plastic bin to be? So plastic bin containing 5 cars, 3 monster trucks. What do I expect for the mean and standard deviation? All right, let's do the mean first because it's the easiest. All right, so I got 1 plastic bin that I expect to weigh 15 grams. I got 5 Hot Wheel cars that I expect to weigh 5.4 grams each. So that's 5.4, 5.4, 5.4, 5.4, 5.4. So just to write that a little bit faster, I am going to do 5 times 5.4. Because remember, multiplication is repeated addition. So if I got to add 5.4 together 5 times, multiplying will make that a little bit faster. Plus 3 monster trucks at an average weight of 9.4 grams. So I got a 9.4, 9.4, 9.4. So I got the 15 grams for the plastic bin, 5.4 times 5 for the 5 Hot Wheel cars, and 9.4 times 3 for the 3 monster trucks. So I'm going to go to my calculator. That's 15 grams plus, and I don't have the numbers in there in front of me. Okay, here we go. So 5 times 5.4, that's for the 5 Hot Wheel cars, plus 3 times 9.4 for the 3 monster trucks. So I get a total of 70.2 grams. That's my grand total expected weight. Now, again, every car, every monster truck, even the plastic bin. So it could be a little more. It could be a little bit less. That's certainly what I expect it to be. But because all of these things vary, there's going to be a standard deviation for that total as well. Okay, so I'm not allowed to add standard deviations. Don't you dare. I'm only allowed to add variance. So let's see here. 0.8 squared. The moment I put that square, now that's the variance for the one plastic bin. Plus, now I have 0.7 squared. That's the variance for one car, but I have 5 of those, so I am going to multiply that by 5. It's 0.7 squared times plus 0.7 squared plus 0.7 squared plus 0.7 squared plus 0.7 squared. So again, that's the variance for 5 cars each. And then I have 3 times 0.2 squared. 0.2 squared is the variance for one monster truck, but I got 3 of those. So I got a variance for the first, 0.2 squared, variance for the second, 0.2 squared, variance for the third, 0.2 squared. So I know that I said not to multiply standard deviation, but I am allowed to multiply variance because multiplying variance is just repeatedly adding it together to speed up the process. So that is my total variance, but I need a giant square root around all of that variance to get me back to a total standard deviation. All right, so here I go. I'm going to do a giant square root on my calculator. So I'm going to do 0.8 squared. That's the variance for the bin. Plus 5 times 0.7 squared. That's the total variance for 5 Hot Wheel cars. Plus 3 times 0.2 squared. That's the total variance for 3 monster trucks. And I get 1.792. So 1.792 total grams is my total standard deviation. So in this plastic bin, I got 5 cars, 3 monster trucks. I expect the total weight of that plastic bin with the cars and trucks to weigh 70.2 grams. But because every one of those objects varies a little bit, the total could be a little bit more, could be a little bit less, and that's where the standard deviation kicks in. All right. That's it for combining random variables. Hopefully it was a fairly short video for a really big, important topic, but hopefully you understand at the end of this, working with means is so easy. Standard deviations is where you got to really focus on those 3 rules. All right, that's it. Hope you liked it. Talk to you later.